right, good afternoon. So let's take a look at the structure of caffeine in 3D. Isn't that kind of cool? Because caffeine is everyone's favorite molecule. I never start the day without caffeine. Let's go to the PubChem database and we're going to search for the structure of caffeine. Spell it correctly there. There's caffeine right here. Let's go ahead and download this. Here's an aromatic compound, and let's just kind of say, what does it tell us about caffeine? So here's the molecular formula, C8H10N4O2. Here's some other synonyms. It's also called methylbromine. I've never heard of the other one. I guess trimethylxanthine, that's another one. Its molecular weight, 194.19 grams per mole. It's an odorless white powder, or white glistening needles. Has a bitter taste, but makes a lot of our beverages taste, well, it wakes us up, right? It's odorless. And so this tells you a little bit about caffeine. It's found commonly in coffee and tea. There's its two-dimensional structure. And we have the 3D structure as well. Usually to download the 3D structure, I like to just go here to the SMILES code, which is just a one-dimensional representation. And I'm going to cut and paste that. Well, cut that. And then we go into Mo. I'm going to paste the SMILES string here. Click the smiley face. And here is everyone's favorite molecule, caffeine. Let's go ahead and show our atoms. We're going to give that a ball and stick representation. We can certainly also show the space filling view, and you can see it's a planar aromatic ring, so everything's all in plane. So that's the 3D structure. Now, in 3D, this is where things get very interesting, because what we can also do is we can also use 3D glasses, right? Now, these are passive 3D glasses. These are the same glasses that you have when you go to the movies and you watch, whatever your favorite movie is in 3D. And what it does is there's two channels. So there's a green and a magenta, right? And so when the computer projects the image at you, it splits the image, and there's a green side and a magenta side. The green side goes into one eye, the magenta side goes into the other eye, and then it splits it into each individual eye, so your eyes see two different images slightly separated, and then your brain's able to put that together as a 3D image, right? And so this technology works fairly well over a traditional LCD monitor. There are some, I think on the old CRT systems, we had some more active 3D displays. And so they gave a different view. But the passive displays, they work on most LCD monitors. Now, I've never tried this on YouTube before, so I think it should work, because again, if you're watching this on your phone, your iPad, that's an LCD screen, and so it should work. You should still be able to transmit both of the images just fine, just like you're watching a 3D movie from your television. So let me know in the comments below how that works out. You can buy really nice 3D glasses like this. I think these cost about $8 to $10 on Amazon. You could also, obviously you may have a pair of some of the cardboard 3D glasses that you may have gotten from an old 3D movie or so lying around the house. You can try that if you want. And so let me know how that works. Now, in Mo, what we can do, I'm going to put these glasses on. There we go. And in Mo, these glasses right down here, that switches between the stereo modes, right? So if I click this, you'll notice that they lit up magenta and green. Now, if you're looking at this image now without 3D glasses, that caffeine molecule looks quite, it doesn't look quite as well. You can actually literally see a little bit of a green and a magenta on each side. But as I kind of spin this around, now we can kind of see, and we can even kind of zoom in, and it kind of gets a little bit bigger for us. So we can actually see all the different angles of our caffeine molecule, right? So that is caffeine in 3 dimensions. Now, if we do caffeine in 4 dimensions, what's the 4th dimension? The 4th dimension is time. And so what we can do for that is we can actually calculate a molecular dynamics simulation, right? I'm going to need my force field for this. And if I go to simulations, dynamics, we're just going to call this caffeine. And let's see, what's our time here? I think that's fine. We're just going to do a very short simulation here. And yeah, let's just keep the water on. Here's our time step. And now notice most of the planar parts of the molecule don't really move too much, but they do jiggle a little bit around. You see these methyl groups on the side? Those are free to spin because that's just a single bond. So we have a little bit of spinning going around with those. We also notice is that as we have gone through our simulation, the planar rings, while they are planar and they remain fairly rigid, they move around a little bit. So it's kind of like a little bit of wave. So we see a little bit of fluctuation even between like 2 different atoms of our aromatic rings as well. So it does allow a little bit of fluctuation, but mostly they remain in the same plane. So, and that is the structure of caffeine. I hope you've enjoyed this tutorial, and let me know how you like this. If you like this, go ahead and click like on the video. You can subscribe to the channel if you like more content like this. And feel free to leave a comment, especially if the 3D worked for you and you were able to get that work. Leave a comment and let me know how that worked out. All right? Thank you.